Hi, this is Base. Again, this video is going to be the compilation of interesting and hard questions in Edexcel maths. The A2 level on the mechanics part, I manually went through all of the past papers from 2018 to 2024 and handpicked the interesting one, which can be considered hard ones compared to the other questions. You can find the question paper, the corresponding mark scheme, and my work solutions in the description. Can you please give me a like and subscribe? I am trying to grow my channel every day, so it would be fantastic to get more support from you guys. And if you do encounter any question harder than this compilation, please give me a comment and I'll look into it. I'll create a short and put the link in the description so that this compilation can grow forever. Without any further ado, let's dive in. Okay, here is the first year, 2018, yeah? And the first question that should be interesting is question 8. Okay, so it's about vectors here. A particle P moves with a constant acceleration at time t equals 0. The particle is at origin and is moving with the velocity of that at time 2 seconds. P is at the point A. Yeah, so we get position vector and velocity vector. Yeah, you got to be careful. They're not the same type of quantity here. A show that the magnitude of acceleration of P is 2.5, right? So we got to be careful. And this is just using Suvat. So we know that at t equals 0, this is called the initial velocity. Yeah, so it's that, right? I'm just going to leave the units, yeah? And then at t equals 2, right? So we know that time is 2 seconds. And the position vector is 7. Yeah, that is like the final position vector, right? So we have the initial position vector being at the origin. We have the final position vector being at 7i minus 10j meters. Then we can find what's called the displacement, right? So displacement here is the S. That's what we have. So if I want to maybe, order them in the sense that we can say that this is Suvat, right? So it's SU and VAT. So S is just the R final minus R initial. R is the position vector. So because the initial position vector is 0, 0, so that's basically just 7i minus 10j, yeah? We want to find the acceleration because we want to prove that we don't care about the final velocity, right? Yeah, because it doesn't give us the final velocity. We don't care, we don't know. So you can see now here that we should use the formula of S equals ut plus half at squared because it doesn't have a v. We don't care about the v. The formula without the v, there is only one of them, which is this one. Right? So cutting out the thing we don't know and we don't care about will help you select the best formula. Usually there is just one best formula, all right? So S is just the, displacement there. Note that if this question told you that the starting point or the initial position vector was something else, then you would have had to, subtract and get the displacement vector first, right? U is what? U is 2i minus 3j and time is 2, right? So I just multiplied 2 there. Plus half. Now we want to find a, and that's a vector there, t squared. So 2 times 2 is 4 here, yeah? And now we just use algebra to solve for the vector a. Note that there are I components and j components here, so you got to be careful. So just multiply out. I have, so this will be 4i minus 6j. Yeah, and this is 2a, right? Sorry, that should be a plus there. Okay, and let me just increase the size a bit, yeah. And here we have still 7i minus 10j. Okay, so we're going to subtract. So 4i subtract 7i, we get 3i. And then minus 6j subtract minus 10, we get minus 10 minus 6. So that's minus 4j. Divide by 2 to get a vector a, right? Yeah, so vector A is just going to be 1.5i minus 2j. And we want to prove that the magnitude of acceleration is 2.5. So we want to find the modulus or the magnitude of A being a Pythagoras of those two components. And you should get 2.5 because that will add up to 6.25, right? And that's just 2.5 meters per second squared. All right, as required here. So that's part A done. Yeah, so you got to be careful there. Okay. At the part B, at the instant when P leaves the point A, the acceleration of P changes so that P now moves with a constant acceleration. Okay, so point A is just that point, right, that we got earlier where the position vector was 7i minus 10j, right? And now it changes acceleration from that point onwards. At the instant when P reaches the point B, which is our new point, the direction of the motion of P is northeast. So northeast, well, if we plot roughly, that's the origin maybe. And where's point A? Point A was 7 minus 10, so 7 minus 10 is around maybe, I'll make it here. This is 7, this is minus 10. Just I and j there. And this was point A. And now, reaching point B, so the direction of motion of P is northeast. So whatever point B is, let's say point B is here maybe, all right? And the direction of motion of P, which is the velocity vector. So when it talks about direction of motion, you should refer to the velocity vector, is northeast. So north and east is like that, velocity. You should know that northeast, when it doesn't say anything else and it just says northeast, it is exactly 45 degrees to the horizontal. So it is making a 45 degrees here to the x-axis. And that is the direction of velocity vector. So we know that the I and the j component are exactly equal to be, pointing towards northeast, right? So we know that for v here, yeah, the I and the j component are equal. So I'm just gonna do like the vector v here is just like ki plus kj, maybe meters per second. All right. Now, because we have still an acceleration, right? And we also need to know something about velocity, right? And we want to find the time it takes. So what are the characters here? We have a change in acceleration. Let's bring SUVAT again. So SUVAT. Actually, you don't need to write them all down, but I mean, just for the sake of explaining here. So we have u, right? Because we can find the initial velocity at the point A, right? So we have u. And actually we can, what is it? Well, we haven't got it yet, but we can find it, yeah? V is the final velocity here. Well, I can write ki plus kj. Yeah, so that's a tick. And A, yeah, given to be 4i plus 8.8j, right? And t is what we want actually, so we must include it. So here we don't care about the displacement because it doesn't ask for displacement. We don't know. I mean, we could know, but we have to do some work, which we don't want to, right? We just want to do the work that is worth it because we want to find time. So you already see that the equation applicable for this is just v equals u plus at. Yeah? Okay, so just to find t there. So we need to know the final speed at point B. Well, actually, we kind of discussed about it. It's like we actually don't know it. It's just ki plus kj, where k and k are to be the same, right? And then what is the u? Well, we do need to find u. That was the velocity at point B, right? So the velocity at point B back then, yeah, when we did part A, at point A, sorry, was found by also u plus at. But the u, yeah, when it was at the origin was 2i minus 3j. And the a was what we found earlier. So we just need to find this initial speed to be used in here, yeah? And the a was 1.5i minus 2j, yeah? That was the speed, the acceleration from the origin to point A. And the time when it reaches point A was 2 seconds. So just put 2 here. That will give us the speed at point A to be used as this term, yeah? Substituted in that term. So what would that be? Well, okay, so if we simplify that, we get for the I component, is just 2 plus 3, yeah, because to expand into the 1.5i there. So I get 5i, right? And then for the j component, it would be minus 3 minus 4, so that's minus 7j, right? Okay, there you go. So that is the velocity at point A, and this should come before that VUAT equation there. Now let's plug that into the equation. Now we have 5i minus 7j for the initial speed at point A going to point B, which acceleration changes to 4i plus 8.8j times the time in which we want to find that. Okay, so if we simplify the algebra here, separating between the I and the j components, we get 5 plus 4t for the I component, and then plus minus 7 plus 8.8t for the j component. It is easier to see it this way, right? Because you separate the I and the j components. They are the basis vectors, okay? Here you can see that because the I component of the right hand side must be also equal to k as well as the j component, right? So this one is equal to k, this one is also equal to k. You can directly equate these two because they must be equal. Each of them is equal to k, so we can say that the I and the j component are just equal, right? So I can just put them in the same equation here like this, so that we solve for t, right? So moving things around, I have 12 here on the left, and 4 subtract 8.8, we get 4.8t, yeah? So if I use a calculator to solve for that, okay, so 12 divided by 4.8, that's 2.5. So t is 2.5 seconds. Okay, that would be the answer there. Let's have a look at the next question, number 10. A boy throws a ball at the target. At the instance when the ball leaves the boy's hand at the point A, the ball is 2 meters above the ground and is moving with the speed u at an angle alpha above the ground. In the subsequent motion, the highest point reached by the ball is 3, right? So from 2 meters to 3 meters, that's 1 meter displacement, right? Above the ground, the target is modeled as being the point T, as shown in figure 4. The ball is modeled as particle moving freely under gravity. Using the model, A show that. Okay, I believe this is missing an alpha here, right? Okay, so we're going to show that first. So we're going to take the vertical motion, right? Because we have quite some information about it. So if you use SUVAT, yeah, so S is just 1 meters upwards. U is going to be U sine alpha, right? You resolve the U component to the vertical. That's going to be upwards as well. V, well, when you reach the maximum, V is 0, right? A is going to be minus G, yeah? And T, we don't know, we don't care, so nada, that's fine. The equation to do this is the one without the T. You think about it. You should recall that it's just this guy. Yeah, so the V squared equals U squared plus 2AS. So V squared is 0, U squared is U, the capital U sine squared alpha, because sine also squared there. Plus 2, and then G here is a minus, yeah, and S is just 1. All right, I think that's gonna lead us to the right expression there. So if we make U squared subject, we get 2G, subtract the other side, and then over sine squared alpha. So that's not too bad. Okay, part A done. Part B. The point T is a horizontal distance of 20 meters from A and is at the height of 0.75 meters from the ground. The ball reaches T without hitting the ground. Now, we're going to consider from point A to T now, not A to the highest point. B, find the size of the angle alpha, right? So we're going to find alpha here, and it's 9 marks. That's not little there. Okay, so surely though there's going to be quite some algebra here for you to do. All right, so we need to consider point T. And it says this is at the height of 0.75 from the ground. So that means from A to T, if we consider the vertical motion, yeah, vertical from A to T, right? What would be the displacement? Displacement, if we again consider downwards as negative and upwards as positive. So from A down to T, yeah, vertically down, right? Because from A to the ground is 2, but from T to the ground is 0.75. That means from A, which is around here, to T would be 2 minus 0.75, right? I'm just going to write here, which is 1.25, yeah? And U, well, the initial speed from at A would be the same as U sine alpha, right? U sine alpha there. And also the velocity, do we know it? No. Do we care about it? Probably not, because we want to find the alpha. So I'm just going to leave that as a cross first. A, yeah, we always have a minus g here. Okay, downwards, minus g. And T, well, do we know it? Probably not, but we can do something because we got T earlier to be, did we? Yeah, from the earlier work here, sorry, not this one. The horizontal motion. Yeah, no, we didn't get it. Okay, that's fine. I thought we did. So the horizontal motion was, in this case, 20, right? Equals U cos alpha times T. So we can link to the horizontal motion. So T equals 20 over U cos alpha. Okay? U cos alpha being the initial speed along the horizontal direction times T, which is the same time here as being T here. So I'm just going to write here 20 over U cos alpha. U being the capital U there from the question. Okay? So now we can see that we have the S, the U, the A, and the T. And that will form the Suvat equation of this one. Yeah, where there is no V. Okay. So note that S here is going to be negative, right? So I'm just going to, this is just the size of the displacement downwards. So I'm just going to write down here as well. But because A is above T, so it's moving down, it's displacing down, so we need to do minus 1.25, all right? Because we are conventing upwards as being positive. So this is equal to U, which is U sine alpha. T is just, yeah, we're going to use that because we are eliminating T, plus 1/2 minus G times also another T squared, right? So that's just that. Okay, some algebra there. Okay, so let's see. The U cancel here, so we get minus 1.25 there. Sine over cos is tan, so I'm just going to write 20 tan alpha here. Okay, and that's also a minus 1/2 G, so 2. Ooh, okay. So what do we have here? This is 20 squared over U squared cos alpha, right? So this will be 400. Divide by 2, we get 200 G here. Yeah. And then down here we have U squared cos squared alpha. What is that? So earlier we had U squared equals 2G over sine, yeah, because U squared equals 2G over sine squared alpha. Yeah, that's why they asked you to prove earlier here, because we're going to use it. Yeah, we're going to use it. So if we sub U squared there, being that into this U squared, yeah, we're going to simplify that quite a bit. So 200G, right, divided by, so U squared is 2G over sine squared alpha times cos squared alpha here. Yeah. So the G cancel there, and this is 100. So down there you have cos squared over sine squared. Well, that's cos squared, right? But it's at the denominator. So when you flip it up, it's going to be tan squared alpha instead. So I'm just going to write again 20 tan alpha minus So this is all 100 tan squared alpha, right? Now this is giving you quadratic, right? That's why it's 9 marks, right? So that's why I picked this one. Okay, so 100 tan squared alpha minus 20 tan alpha, yeah, minus 1.25 equals 0. Okay, so we can solve for that. So if we do tan alpha equals minus b plus minus square root b squared minus 4 times a times c, yeah, we need to show some working, right? Divided by 2 times 100. But we're gonna just use a calculator. Everyone has a calculator there. And we can use a quadratic solver here, putting what? 100, enter, minus 20, enter, and then minus 1.25, enter. So this is going to be what? X1 is minus 1 over 20, comma, 1 over 4. Yeah, so we're going to reject the negative because this is, well, if we have a negative, then the angle will be like obtuse, which is not possible here physically. We are throwing forward, not backwards, right? Okay, so tan alpha will be 1/4. Yeah, and then if we go back to the calculator mode and arctan 1/4, that will give us 14.0 degrees. Yeah, that will be the answer there. Okay, but we keep in mind we have tan alpha being a quarter too. Maybe we're gonna make use of that later. Might be useful, who knows. Okay, so part C, state one limitation of the model that could affect your answer to part B. Well, usually you read the question. If they don't say yet that they ignore air resistance, then that's the target. Because usually air resistance is a big deal when you throw quite far away. We're assuming this is far, like 20. Particularly if the ball is light. Yeah, if the ball is light, like light object, air resistance will become a big deal. Okay, now, so because they don't include it here, so the model doesn't account for air resistance. Yeah, and that is the big deal. So it might affect the value of alpha. So because when you measure that you've gone by the distance of 20 meters, and you use that information to back calculate the angle, assuming that there is no air resistance. But in actuality, there might be. So the alpha there will change. For example, if you assume that there is no air resistance, but actually there is, the alpha should have been bigger, right? Because when you slightly increase the angle alpha, it's going to go further away. But actually, this makes you go just like 20, including air resistance. So if you didn't include air resistance, it would have gone further than 20. That means if you think about that backwards, the alpha you got is actually an underestimate because it should have been bigger to go further, right? Something like that. Okay. So yeah, that would be my answer. But there are other aspects too, like because we say that the ball here is a point because it says here being the point T, right? So what's wrong with being a point? Well, when you assume something as a particle, you don't include the shape. Now, what's wrong with having a shape then? Well, the shape can do a lot. For example, if my pen here were to be thrown and then it rotates, when an object rotates, it has something called rotational kinetic energy, right? This is a bit physics, but that will make the calculation a bit inaccurate because the fact that it has rotational kinetic energy will make like the energy transfer not perfect, because when you do perfect suvat in the projectile motion, that assumes no such motion here. It's only just a point going forward, right? So for example, it might go not as far because there is some energy here need to be spent to make it rotate like that. If you include air resistance and there is a shape here, that shape will interact with the air resistance as well. So the shape can do a lot of things, right? And that will be the source of error there in the model. Okay, so that's part C. Part D, find the time taken for the ball to travel from A to T. So from A to T, right, it's still the same 2 points. So we can just use the information we got earlier. Let's see. Okay, so to calculate time, what should we do? Yeah, how about we use this one? Because we already know tan alpha, right? And u will just be easily, okay. So because time is just 20 over cos u cos alpha, right? Yeah? But we also know that u from the thing we proved in A, right, is just square root 2g over sine alpha, because down there we have sine squared. So if you square root that, the up one will be, the numerator one will be square root 2g. And that would just be sine alpha. So if you plug that in to the same, to find t, plug that in here, you will get what? Square root 2g here, and then divided by sine alpha, and this will just be the same as cos alpha here. Yeah? So again, do you see that this is a cot alpha again? And then when you flip it up, it becomes a tan. So this is 20 tan alpha divided by root 2g. And we remember that tan alpha is just 1 over 4. We're not going to use the angle now, because that's why I kept it, yeah? Because we might use it later. Yeah, it's good to keep the exact form, yeah? And then divided by root 2g here. All right, so our answer should be accurate. So that's just 20, fraction 20 times a quarter divided by root 2 times 9.8. Yeah, so that's just 1.13 second. Let's do a second here, yeah? That would be my answer to part D, and that's it. Let's have a look at the next year, June 2019, for mechanics, all right? The first question I think should be interesting is number 3. Yeah, so we have connected particles here. You can read through the question, all right? Now, I'm just going to go with part A, show that T is 12 mg over 5, and it's 8 marks. So, by the looks of the marks here, I think it is probably a full force diagram solving, right? So, you just do force diagrams for A and B, yeah, and then you just solve for the tension. And you probably will get also acceleration. If they haven't given you the acceleration, maybe you need to solve for one as well, but let's see how it goes. So now let's have a look at the both object, right? Let me write down June 2019. This is question 3, part A. Yeah, so for object A, we have the mass of 2m. The force acting up is tension. And then the force acting down, you should know that when you have an inclined plane like this, the force acting down should be mg sine alpha. If alpha is the inclination angle of the slope, then it is always mg sine alpha. Yeah, and m here being 2m actually, right? And the force acted perpendicular to the plane from the weight. Yeah, we are talking about weight components here. So this is 2mg cos alpha, right? So that's going to be the same as the normal reaction here. We get this because we want to know something about the friction. And if you read the question, it's given you the coefficient of friction, yeah, being 2 over 3, right? So the coefficient, the friction here will be mu, which is 2/3, times 2 mg cos alpha. Because we know that along this perpendicular direction to the slope, there is no resultant force, so it's just n equals 2 mg cos alpha there, right? So the friction is now 4 over 3 mg. Now, because it's given us also that tan alpha is 5 over 12. So if you do a little right angle triangle here, this is alpha, 5 over 12 like that. Yeah, that's faster. You don't need to solve for alpha at all. And then you know that by a Pythagoras, and then the hypotenuse is 13. So that means cos alpha here would be 12 over 13. just getting by that triangle there. And if I simplify this, I get 16 over 13 mg. That's the friction, right? Yeah. Now, then we do sigma F equals ma for this object, for object A, yeah? It's just going to be T minus, right? Because it's probably pushing up and then B is moving down. T minus 2 mg sine alpha would be 5 over 13. Minus F would be that, because we already got it, yeah? And then equals ma. So, wait, hang on. I got 2 ma right? Tension 2 mg minus 2 mg. Yeah, I think I'm fine with that. And then equals 2m, because the mass is 2m, and then times the acceleration. Yeah, so that's the tension there. If we simplify, yeah, we get T minus, what's that, 10 over 13 minus 16 over 13. So that's actually 26 over 13, which is 2 mg, equals 2 ma. Let's say that is equation 1, right? Okay, so for the particle B, the block B, right? Sigma FB equals, because it's moving down, yeah? Because it's moving down, so we're going to do the weight of B, which is 3 mg, minus the tension, now equal the mass of B times the acceleration, yeah? Now it seems like if we add them up, right? If we add up equation 1 and equation 2, T will cancel first actually, so you get what? 3 mg minus 2 mg, that's mg, equals 5 ma, right? So actually, sorry, A here. So actually A is just g over 5, yeah? And T will just be 2 mg plus 2 ma, which is that, because we just got A. I'm using equation 1 here. So that is just what? 6 over 5 g times 2m, which is, yeah, 12 mg over 5 as required, right? That's just my working there. Okay. Next one, part B. After B reaches the ground, A continues to move up the plane until it comes to rest before reaching P. Okay. Okay. Determine whether A will remain at rest, carefully justifying your answer. So when it is now come to rest, it might go down. I mean, it's like it's just throwing something up, it will go down, but in this case, you push it up, like it was pulled up by the string, and then B reaches the ground, right? And then somehow the string becomes slack because they are no longer connected. So A will have some inertia continuing to move upwards. And depending on the friction, it might stop somewhere. In this case, it will stop. But after it briefly stops, will it move down, back down, or will it stay there? We need to find the friction compared to the weight component. Yeah? So when it stops, the weight component is still mg sine alpha. Yeah, so that's just sine alpha was what? 5 over 13, right? So that's the weight component. Yeah, and the friction, right? The coefficient of friction. So we can use the same coefficient of friction here, which is 2 over 3. So friction F equals mg. Wait, hang on. It should be 2, right? This is 2. 2 mg, yeah. So that should be 10, yeah. And then the coefficient of friction mg here, mg 2 mg cos alpha times the coefficient of friction 2 over 3. Yeah, so cos alpha was 12 over 13, right? So that's 2 mg 12 over 13 times 2 over 3. Yeah, just simplifying all that, we get what? 3 cancelling with 12, we get 4, so that's 16 over 13 mg, right? Because 16 over 13 mg is greater than 10 over 13 mg. Yeah, this is the friction side, the maximum friction. So max friction here, and this is weight component. So when it stops up there, there are only two competing forces, the weight component pulling it down or the maximum friction keeping it up, right? So if maximum friction is greater than the weight component, then it's not going to move down. So therefore, A will stay at rest, not moving down, right? Yeah? So we already justified our answer. Next, part C. Suggest 2 refinements to the model that would make it more realistic. Well, how do you make this more realistic, right? Well, first thing first, you assume a lot of things. You assume that the string is inextensible, right? So that should be first, string extensible, and second, the pulley, you assume that it was smooth. So if you account for the friction on the pulley, then the tension on either side might not be the same, right? So refinement is, if we consider friction from pulley, yeah, and then second, that would make it more realistic. Yeah, I'll just say string can be stretched. Yeah, I'll go with that. So that's it. Next question, number 4. All right. What do we have here? A ram AB of length 8 meters and mass of 20 kg rests in equilibrium with the NA on the rough horizontal ground. Yeah, so now you have a ram resting on a rod, probably. The ram rests on a smooth solid cylinder drum, which is partly under the ground. Okay, as shown there. It's like sinking in the ground, the gray ground there. The drum is fixed with its axis at the same horizontal level as A. The point of contact between the ram and the drum is C, where AC is 5 meters. Okay, we can see that as shown. The ram is resting in a vertical plane which is perpendicular to the axis of the drum. Okay, yeah. At an angle theta to the horizontal, where tan theta is 7 over 24. The ram is modeled as a uniform rod. A, explain why the reaction from the drum on the ram at point C acts in the direction which is perpendicular to the ram. Now let's draw out a diagram, right? So if we have a ram looking from the side here and the drum looking from the side as well. So, I mean, when you are resting something like a ram here on something else, of course they have normal reaction to each other, but as well as normal reaction, there might be also friction. It's like, for example, if you if let's say this thing is smooth, right? Let's say this is smooth, okay, and let's say the center of mass of the ram is somewhere here. Of course, if you let go of that, it might slip down. It might slip down, right? Now, because it could slip down, there is like an applied force or a force that attempts to make it go down. So maybe there's going to be friction. Yeah. Now, if there is friction, let's say if there was friction, but in this case, the drum is smooth. Actually, it says that the smooth solid cylinder drum here. Yeah. So, but let's say there was friction. Okay, and this is normal reaction, and this is friction. Okay, now normal reaction and reaction can be different because normal reaction is a single force perpendicular. But in this case, it uses reaction. That means it is the resultant force from the drum to the ramp. So if there was friction, the resultant force would have been that. Yeah? And that is not perpendicular, right, to the ramp. But if there is no friction, and of course there is, that's the case, then you don't have any component of force acting along the ramp. That means the R will still be the same as the N. So N here is normal reaction, and R is the resultant of the reaction, where it take into account the friction as well. Okay, so I'm just saying here that because there is no friction between the drum surface and the ramp, yeah, it's because there is no friction between the drum surface and the ramp, yeah, therefore no, the resultant reaction is just from the normal reaction, yeah, which is perpendicular to the ramp. Yeah, I'm just gonna write like that. Okay, so that's part A. Part B. Find the magnitude of the resultant force acting on the ramp at A. Okay, so now we have something else to consider. Okay, so here the ground is rough, so there will be a normal reaction, yeah, it's the N there, and some friction. Okay, and we have reaction R here. I'm just going to use R for that one. Okay, now this is 9 marks, so we need to be thorough here. The weight of the ramp is probably uniform, isn't it? Is it uniform? Yeah, the ramp is modeled as uniform rod, so the center of mass is gonna be 4 meters away from that point. Yeah, and the ramp is 20 kilograms, so it's 20 G. Okay, so we want to find the magnitude of resultant force acting on the ramp at A. Yeah, so it's just the resultant force between the normal and friction. So we find them separately using equilibrium, right? So let's see. The angle here is theta, right? If we take moment, we're gonna find R first. So let's say we take moment at point A, yeah? This is point A right here. So at point A, we take moment. We don't need to consider the N and the F because we don't know it yet. So we can do like R times the perpendicular distance here is just 5, right? Equals, and then 20G will be the weight, and the distance here will be 4 meters, resolving down cos theta. Yeah? Now because it's given us that tan theta is 7/24. So if you do a little triangle again, I always love to do a little triangle here, 7/24, so that should be using Pythagoras 25. Okay, that means cos theta here is 24/25, right? And then we're going to solve for R, so R is just 5 cancel with 20, we get 4G times 4 times 24/25. Okay, should we keep G there? Yeah, we can. So we get, what's that? Wait, hang on. Just going to use calculator here. So 16, right, times 24 times 24. So that's 384/25G, yeah? Okay, so that's the reaction there. Now we're going to use this reaction to find N and F, right? Again, note that because this is alpha, so that's going to be alpha. If that is alpha, that is 90 minus alpha, theta. So this little angle here would be theta as well. Yeah, if you do geometry there, it's going to be theta here. Why do I need that? Because I want to resolve the r into, you know, horizontal and vertical. Yeah, so let's do vertical first. Fy. Okay, so that's going to be r cos theta, right? This one, the vertical component of r, equals, right? Oh, we also have a plus n there, so plus n equals the downward force, which is 20g, right? Yeah. Okay, so r is already that, and we already know cos, so we know n here. So n is going to be 20g, yeah, minus r, which is 384 over 25g, cos theta, which is 24 over 25. Again, that's a huge number. Okay, so n will be, so I'm going to do 20 minus 385 times 24, 4, excuse me, over 625. Okay, that's horrible number. Hang on, sorry, it's 625 here. G, right. Okay, at least it's not negative. Okay, so that's the n, and then we can use the n to find the friction, because we are given the, no, we don't need coefficient of friction. We can just do fx, right? So from fx here, we know that the friction will just be r sine theta here, which is again 384 over 25g times the sine theta, which is 7 over 24. Okay, so that's that times 7 over 25 times 24, 112 over 25. Let's see. Okay, g as well, right? Now if we want to find the magnitude, yeah, so sigma f on ramp at a equals, yeah, we just do Pythagoras there. So that's in horrible number 3284 over 625g, and then squared here plus yeah, I got that already, 112 over 25 here, and g squared. Okay, and then we're gonna put everything in a calculator, guys. Okay, so I'm just gonna do g outside here because I already got both of the terms having g squared there, so I'm just taking it out, and in the square root I only have so 3284 divided by 625, and then squared, yeah, plus 112 over 25 squared, yeah, so that's about 76.7. I'm just going to keep 3 significant figures there. Okay, that's the resultant force. Yeah. Part C, given that the center of mass of the ram is assumed to be closer to A than to B. Okay, hang on. The ram is still in equilibrium in the position shown in figure 2, but the ram is not now modeled as being uniform. Okay, so right. Given that the center of mass of the ram is assumed to be closer to A than to B, so it's like more to here than before, so this is before, this is after, yeah, and before was still, you know, like that, yeah. Okay, state how this would affect the magnitude of normal reaction between the ram and the drum at C. Okay, so at C it was still this guy right here, R. So how did we get R earlier, right? So R was obtained by doing moments, right? Yeah, we did R times 5. So if the center of mass was closer to A than B, that means this distance right here is smaller. If that distance is smaller without anything else changing, then R would be smaller, right? Yeah, that's it. So Part C, the R would be smaller. That's it, because it doesn't ask for the reason. So we're just looking at how would this have changed the calculation, right? So it's just that one being smaller. So this one should be smaller as well, mathematically speaking, right? Okay. And that was it. Next, question 5. The points A and B lie 50 meters apart, horizontal ground. Yeah, at time t equals 0, two small balls P and Q are projected in the vertical plane containing AB. Right. Ball P is projected from A with speed that at 30 degrees. Okay, everything I think is included in the diagram, but the highlight here, that's why I handpicked this one, because they collide in the air. At time t equals 0, at time t equals 2 seconds, the P and Q collide, yeah? Until they collide, the balls are modeled as particles moving freely under gravity. A, find the velocity of P at the instant before it collides with Q. Well, basically just at time t equals 2. The velocity of P is what, basically, okay? And note that because it doesn't say what component of velocity, so we need to be careful. That means the resultant velocity, right? If it doesn't say anything about either horizontal or vertical, that is the resultant velocity. We might need to give the direction as well as the magnitude just to be safe, all right? So part A here, well, we're just going to take particle P, yeah? And then, well, we have time 2, we have everything for P. We have the speed, we have the projected angle there. So we can use Suvat, right? So let's do the x first. It's Vx, yeah, will be constant at 20 sine 30, right? Just resolving that initial speed to the vertical, to the, that should be a cos, to the horizontal direction. I use cos 30. And that is just what? Cos 30 is root 3 over 2, so that's 10 root 3. Yeah, I'm just going to keep it that first. And then for the y, or the vertical component, then we do Vy equals Uy plus At. And A is, of course, also Ay. So at the time equals 2, right, it's going to be Uy being 20 sine 30 plus Ay is taken as the gravitational acceleration, which is minus 9.8, acting down, and t is 2. Yeah, so we're just going to find that. So this is what? Sine 30 is 1 over 2, so that's 10 minus 19.6, right? Yeah? So that's minus 9.6 meters per second squared, right? So that's, meters per second. That is just the final speed vertically. Now, note that it is a negative sign, so this is indicating that is actually at time equals 2 is going down, right? It's like going down. So the velocity diagram will be something like this. This is 10 root 3, and this is downwards 9.6, right? Yeah, so the resultant velocity should be like that. So just to be safe, right, velocity of P, we have to say the magnitude as well as the direction. Okay, so the magnitude of velocity of P at t equals 2 here is going to be the Pythagoras of 9.6 squared plus 10 root 3 all squared. Yeah, let's see, calculator. So square root of 9.6 squared plus 10 root 3 and then squared. Well, that is just 19.8 meters per second. Okay. Now, the direction, right? So the direction, we can say that it makes a depression angle, or the angle to the horizontal, right? Which is this angle here, yeah? And that angle can be found by theta equals, well, we're doing arctan of the vertical over the horizontal, yeah, to get that. So the vertical is 9.6 divided by the horizontal 10 root 3. Okay, so in degree first, gotta be careful there. And then arctan 9.6 divided by 10 root 3. So that's 28.99. If I round that to 3 significant figures as well, it's going to be 29.0 degrees. Okay, so it's going to be 19.8 meters per second at 29.0 degrees downward from the horizontal. Yeah, like that. 29.0 degrees. Okay, that is the answer then for part A. Part B, find the size of angle theta, yeah, and the value of u. Right, now we got to incorporate the other object now, the object q, the particle q. So the size of angle theta is from the q and the value of u is also from the q. Now we know that they collide at t equals 2 seconds, in which the vertical displacement of p and q will be the same, right? And we also kind of know the horizontal displacement of q. We can just find that by knowing the horizontal displacement of p, and also the fact that the sum of the displacement from left to right and from right to left from where they meet is going to sum up to 50, right? So for q, yeah, we know that if we do the horizontal displacement Sx for the q, it's going to be the initial speed u cos theta times t. Yeah. Well, we also know the number here because we can calculate the horizontal displacement of p. Yeah. Well, let's do that first, right? Let's find the horizontal displacement of p. Yeah, we just got the speed there, so we didn't get much. So for p first, right? Sx is just equal to, it's just 20 cos 30 times 2. Yeah? Well, that will be, cos 30 is again root 3 over 2. So that's 10 root 3 times 2. So 20 root 3. Yeah? And Sy for p will be, well, we can do u plus v over 2 times t, right? So u is 20 sine 30 again, plus v. Vy was just the horizontal component, was minus 9.6, right? Yeah. So I'm just going to do minus 9.6 here over 2 times t, which is also 2. So that's going to cancel to be, 2 cancel. We get 10 minus 9.6. That's minus, not minus actually, 0.4, right? 10 minus 9.6. Yeah. So actually it's just gone up by 0.4 meters. That's not high. Okay, so after getting the data from P, we know that to make this make sense, right? Where the place where they meet should be, from point A to the right by 20 root 3 meters. That means the displacement of particle Q from the right or from point B should be 50 minus 20 root 3, right? We know that for a fact. And also if we compute the equation of vertical displacement of Q, we also know that's going to be equal to 0.4, right? So I'm just going to say 0.4 here already. 0.4 equals, right? So let's use the u sine theta times t plus half a t squared, and t is also 2, yeah? So t is 2 here, right? And then t squared, so times 2 squared there. Now, I forgot to simplify the first equation there because actually you also know time being 2 there. So here we have u cos theta then equals to dividing both sides, I get 25 minus 10 root 3. Gonna keep that as that because then we can do something with the other equation and then I get u sine theta here. So if I make u sine theta the subject for this vertical component here, I'm gonna get what? 0.4, that's times 2, yeah? This is gonna be a negative term, so if I move to the other side, it's gonna be a plus. And what is that? It's 2 times 9.8, so that's 19.6, right? Divided by 2, because we have the 2 times u sine theta there. So just undoing that. Let me double check this. Yeah, I think I'm okay with that. So that's going to be 10, isn't it? Yeah, because 19.6 at 0.4 is 20, divided by 2 is 10. So now we have both u sine and u cos. We can find the angle, right? So if we divide u sine theta by u cos theta, it's going to be 10 divided by that, which is tan theta, isn't it? Because u cancel and sine over cos is 10. So that means we can do arctan to solve for the angle theta first. Arctan, just keep that, 10 over 25 minus 10 root 3. Yeah, so that's going to be theta equals 52.5 degrees. Yeah, and then we can find the mu as well. Just plug it in one of those equations. So if we plug theta into sine here, we can find the mu. Sorry, the u. So that is actually part I there and part I here. So u equals 10 over sine theta then, which is just the angle we got earlier. So I'm just gonna keep that as answer first. Wait, what? And then I do 10 over sine answer. Yeah. So that's going to be 12.6. Yeah. That's the u. Okay. So that's part B. Next, part C. State one limitation of the model other than air resistance that could affect the accuracy of your answer. Okay. So here it says clearly that we should not mention the air resistance. Now, usually when you assume that objects are particle, right, because they are modeled as particles here, moving freely under gravity. Well, what's wrong with that? Particles don't account for volumes or shapes of objects. And what's wrong with having shapes? Well, when you have shapes for objects, they kind of like have some extra types of motion like rotation. So in the air, depending on how you rotate through the air, the resulting kinematics can be different. For example, if you rotate a lot, you may not go as far because some of the energy will be spent to make you rotate. If you go like streamline, don't rotate, through the air, you're gonna go far. You're gonna go farther, right? But if you do something else, right, energy will be shared for that rotation or movement in the air. So I'm just saying here that because the limitation is that it doesn't account for the shapes or volume of objects, right? A and B. Yeah. So the distance traveled can be different, right? Other than this, you can also say like, it doesn't account for the wind, like the gust, not the air resistance, but like actual wind, that would make the ball like a little shifted along the trajectory. But that's kind of like unreliable, as in you may or may not have the wind, but when you ignore the shapes here, it is already very inaccurate in that sense. Like the shapes do a lot of things into the kinematics of the particles, all right? And other things like, well, you can also say something about the g value being not like absolutely 9.8. It might be something else, but that is a minority, right? That is like a minute like effect on the actual accuracy of the model. But the fact that, apart from air resistance, actually air resistance is the most dominant assumption here. But then other than that, it's just, yeah, what I said, the wind, the shapes, etc. Right? Okay. Let's have a look at then the next year, October 2020. Right? So let's see what I got for you. Number 3. At time t seconds where t is greater than or equal 0, a particle p moves so that its acceleration a is given by that. And that is a vector where it depends on time. So this is not a constant acceleration motion. We should use kinematics, right? Where we can use calculus to find velocity by integrating acceleration. So at time t equals 0, the velocity of p is 36I. A, find the velocity of p when t equals 0. Sorry, t equals 4. So A, we're going to integrate that. So, and note that when you integrate A, this is just the change in velocity. Yeah, change in velocity is integral A dt. Yeah, if you want final velocity at time t equals 4, then you have to add the initial velocity, right? But we're going to integrate this first. So we integrate that, we integrate the two components separately. You can write like this. I mean, I actually prefer in a column, but I guess you might want to do like this. Okay, so I'm just going to write like this, like separate component I and j. Okay, so if we integrate that separately for the I component, we get t here, and integrating 4t, we get 2t squared, right? Yeah, I. All right. And then for the j component, we get 3t minus t cubed over 3, right? And if we sub the bounds in, it's 0 to 4. That's going to be a change in velocity across the 4 seconds there. And if we just sub in for both components, we get 4 minus 4 squared is 16. 16 minus 16 times 2 is 32. Yeah, that's the I. But then if we sub the 0 in as well, yeah, in the two terms here, we're going to get 0. So that's minus 0 for the I. And then for the j, right, this is a j here, subbing 4 in, we get 12. So that's 12 minus 64 over 3 and minus 0 for the other limit. So that's just minus 28I. And then what do you get here? Well, 36 minus 64, that's minus 28 over 3j. So that means v at t equals 4 would be just adding that 36I meters per second to the right component, which is the I component here. And then the j component doesn't change because there's nothing for the initial velocity there to add it. So this is just what? 8, right? 8I minus 28 over 3j meters per second for the velocity at t equals 4. Yeah, so that's part A done. Part B, find the value of t at the instant when p is moving in the direction perpendicular to I. Okay, so if you don't know what to do with this, then you might be in trouble here. The direction, this is moving into direction perpendicular to vector I. Vector I is just to the right. Yeah, so we need to get the equation of velocity first at time t. Okay, well, we're just going to get v0, which is the initial velocity, plus delta v that we got earlier. Yeah, so the v0 is just, again, 36I. Yeah, but delta v here, we're just going to take this without subbing in the bounds, right? So, but, I mean, instead of subbing in 4 here, it's just going to be a variable t because we don't know the time yet. So we're going to keep that as t. So in fact, it is actually just this guy because the lower bound here doesn't do anything to alter the form there. So it's just t minus 2t squared I plus 3t minus t cubed over 3j. Yeah? So that's the delta v with respect in terms of time. Okay? So when it says moving in the direction perpendicular to I, right? That means it is parallel to the j. When it's parallel to the j, it means the I component should be 0, right? So the I component is 0. We can say that we're going to take that one as well. So 36 plus t minus 2t squared should be 0. Got to be careful here because it says perpendicular to I. That means it's parallel to j. That means it doesn't have any I component, right? Okay. So let's do 2t squared minus t minus 36 equals 0. And then I'm going to factorize this, hopefully. So let me try 4 and 9. 9 and 4, I mean. So what's that? Yeah, that's minus t plus here. So t is just 9 over 2 and minus 4, but we reject negative time. That doesn't make sense. Okay, so the time here is just 4.5 seconds, right? Yeah, as the answer for part B there. And then part II, at time t seconds where t greater than or equal 0, particle q, another one now, moves so that its position vector, r meters, relative to a fixed origin, O, is given by that. Okay? Find the value of time at the instant when the speed of q is 5. Well, this is another particle. Doesn't have anything to do with the particle p there. We want to find speed from position vector, right? So we differentiate the position vector, okay? So v equals dr by dt, right? So that is just differentiating separately for each component. We get 2t minus 1 for the I and plus 3 for the j, yeah? And then we want the speed. So this is velocity at time t, right? So the speed is doing the Pythagoras for both components. So it's just that. Yeah, this is the speed at time t. But we know that we have to equate that to 5 because it's telling us that the speed of q is 5. So I'm just going to equate that to 5. To make the algebra easier, we square both sides, right? Yeah. So I'm just going to make this 9, and that's just 25. Okay? There is no need to expand the complete square there because we can just rearrange and solve t by just, undoing from outside in, and then you're going to get t. So if you don't know what I mean there, it's just this first, right? Subtracting 9 both sides, and then squaring both sides, right? I get plus minus 4. Well, the minus doesn't make sense because you're going to get a minus time. Then I'm just going to say 4 here and minus 4, but rejecting minus 4 there. Time is then equal to 4 plus 1 over 2 is 2.5 seconds, right? Yeah? So that is the value of t, 2.5 seconds. Answer, okay? Let's have a look at the next year, October 2021, for the mechanics. All right, so the first one I picked should be question 2. This is October 2021, question 2. Yeah? I mean, the connected particles is usually interesting. So there you go. Small stone A, 3m, small stone B, m, attached to the string as shown. So usually, for the whole lot of text here, it's just saying, according to the diagram. We just selectively look for the numbers there, like the tan alpha. Yeah, it's given the angle there. But we're not going to use the alpha directly. We're just going to use the ratios, right? The string passes through pulley and the other modeling assumptions. Now we note that there is also a coefficient of friction here. Okay, stone A is released and begins to move down the plane. Now you got to note that this is moving down the plane, not the other side, because, well, maybe it makes more sense to, to have a heavier mass pulling down like that, right? And then in part A, using the model for the motion of system before B reaches the pulley, write down an equation of motion for A, right? So just for object A there. Well, classically, when you have a particle on an inclined plane again, there will be a weight component down the slope, and this is mg sine alpha, but m is 3m, so it's 3mg sine alpha, like that. And then the weight component perpendicular to the slope, and that is just 3mg cos alpha, just the opposite. And then the normal reaction which will be used to find the friction, and the friction itself acting up. But note that we also have the tension. Okay, I mean, I don't know which one is greater, but for the sake of ease of looking at the diagram there. Okay, so let's compute the force equation, like the sigma F equals ma, the Newton's second law equation. Yeah, and that is called equation of motion. So don't confuse that with SUVAT, right? The equation of motion is just basically Newton's second law. So sigma F equals ma. Yeah, we gotta make the downward force down the slope positive here because it's moving down. So I'm just gonna do 3 mg. Well, about the sine alpha thing, yeah. So if alpha is this angle, because we're given the tan alpha, so that should be 3 and 4 here, because that is O and A, and then we have a 5 here from Pythagoras. So that means the sine alpha would be 3 over 5 easily. Yeah, I've used this trick before. You might have seen it already. And then, so that's gonna subtract F, right? F is mu n, so mu is 1 over 6, and n is just 3 mg cos alpha, which is 4 over 5, right? So I'm just gonna write the whole lot of that down first. Yeah, minus the tension equals m, which is 3m, and then a. Gotta be careful there, numbers are tricky here, right? And then we just simplify the left hand side, so it's just 9 over 5, and as you can see, these are terms with mg, they are like terms. So let's simplify this. That's 2 cut 4 is 2 over 5 there, so that's 9. Yeah, 9 minus 2 over 5, right? Isn't it? Yep. Minus t equals 3 ma. So that's just going to be 7 over 5. I forgot mg here. Mg minus t equals 3 ma. So that's the equation of motion of particle A. Now, that is just part A done. So let's do part B. Part B show that the acceleration of A is 1 over 10g. So we need to use the other equation of motion from the B particle, right? And the B particle, well, if I have some space here, I forgot to draw the whole system. But beta particle is just having a tension T here. So the pole is around here, yeah. And the mass of particle B is just m, so that's mg. But it's going up, right? Because A is going down, so B must be going up because they are connected. So sigma F equals ma again. For B, it's just going up, T minus going down, mg equals ma. Yeah? So if we add these two equations, right, we cancel the t, so it's just going to be 7 over 5 mg minus mg because the t's cancel there. And then we have on the right hand side, adding these two, we get 4 ma. Yeah? So that is just what? 7 over 5 minus 5 over 5, that's 2 over 5 mg equals 4 ma. So m cancel. So we have what? A equals 1 over 10g. Yeah? And that is just as required. Okay? Yep. C. Sketch a velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley. Explain your answer. So this is actually the interesting part and the core reason why I picked this one, because I have never seen a question in a pulley system asking you to plot like this. Well, it's rare at least. Maybe I might have seen it before, but it's rare. So let's just do it, right? Okay, so the velocity time graph depends heavily on the acceleration. Okay, so let's consider A first. A is accelerating up, yeah, like that. Sorry, down actually. 1 over 10g, fine. But B is accelerating up with the same value. Okay, now we want to sketch the velocity time graph for the motion of B, yeah, from the instant when A is released from rest to the instant just before B reaches the pulley. Okay, So velocity time graph of p, because acceleration is constant, right? So it's from rest, linearly accelerating to some point. Yeah, because we don't know how far it's going to go up before reaching the pulley, so I guess we're going to have to leave the answer like that. Just add some time and it's going to be linearly increasing up to a certain point, which we don't know, and that's the best we can do to sketch this thing out. Okay, so let's discuss about part D. In reality, the string is not light. State how this would affect the working in part B. Right, so usually connected particles, by means of using strings and pulleys, right? They are assumed to have equal tension on either side. Tension on the string. Well, because if you don't have equal tension, that's going to be a little complicated, because at least the tension you use are not going to be the same, yeah, for both objects. Well, could there be a reason why tension might not be the same? Exactly what it's asking here. String is not light. Because when you pull on one side, yeah, let's go back to the diagram. So when you pull on one side, let's say this is pulling down, just as the question there. The weight of the string will be more towards this side. Yeah, so the weight of the string will also kind of like, the weight component of the string will contribute to the pulling down force down the slope. So you might have tension more on this side rather than this side, because let's say this is pulling. You have tension here, yeah. Well, actually, tension is going to be, yeah, up that. But let's consider tension on the pulley, right? So tension on the pulley will be like that and like that, because you also have friction, right? Sorry, you also have weight component on the pulley. So it's the weight component on the string will help pull it down this side, right? It's just the weight component there of the string. So you might have less tension on this side, sorry, more tension on this side, because the tension with the weight component of the string must add up and equal to the tension on this side, right? And that is dynamically changing, because when you have more and more string on the left, there will be less and less string on the right. Yeah, well, you can argue I can also have weight of the string on this side, that's true, but it's changing. The proportion of weight will be changing as you move the particle up and down on the other side, right? So here is the effect, right, it's asking for. So the tension of the tension forces of on A and B, right, are not the same. Yeah, if string is not light, yeah, due to the contribution of weight components. Yeah, so if there's more weight on the left, it will be less tension on the left and more tension on the right, and so on. All right, next, question 5. At time t second, a particle p has velocity v. This is kinematics again. Yeah. A, find the acceleration of p at time t seconds where t greater than 0. Okay. This is not hard. Yeah. It's probably not the reason why I picked this one. Maybe the last one is more interesting. So let's just do it in order. So A, find the acceleration of p at time t second. Okay. So acceleration is just dv by dt, yeah. So differentiating each component, so differentiating the first one, we get half of 3t to the minus 1/2. So that's 3 over 2 t to the minus 1/2, yeah, I, and that's just differentiating minus 2t, we get minus 2j. Okay, that's acceleration, and that is it, because that's what we get. So I'm just gonna tidy up here and make it like 3 over 2 root t like that, I minus 2j meters per second squared. Yeah. Okay. Find the value of t at the instant when p is moving in the direction I minus j. Yeah. The value of t when it's moving in that direction, well, let's say when you see moving into a particular direction, it's just parallel to that vector. Okay, so we say that okay, this is moving in the direction, so it's going to be the velocity vector. Be careful. So we're going to say that v velocity vector equals some k constant multiplied I minus j, because they're parallel, so we can do that. Yeah. So the v is just 3t to the half I minus 2tj equals ki minus kj, right? So that means the 3t to the half will be equal to k, and minus 2t will be equal to minus k. Okay? Where k is to be found. But, I mean, if you simplify the second equation here, you get 2t equals k. So basically, it's just equating these two. 3t to the half equals 2t. Yeah? So if you simplify the power there, so I move 3 over 2 here on the left, and then you divide t, square root t to t there, you get square root t here. Yeah? And then t will just be 9 over 4. Okay? Which is 2.25 seconds. Yeah? So that's just the time when p is moving in the direction that. Okay? At time t seconds where t greater than 0, the position vector of p relative to a fixed origin O is r meters. When t equals 1, r is minus j. So this is asking you to find the position vector from velocity. Okay, so we're going to integrate, right? So let's just move down. But note that that is just the change in the displacement, the change in position vector, if you like. So this is delta r. It's just going to be given by integral v dt. Yeah. Just like I did earlier, when you integrate a dt, you get change in this change in velocity, not velocity itself, right? Just have to be careful there. So we're going to integrate this to get the change in velocity, and then we're going to plug that to find the the r in terms of t there. So change in displacement, we're going to find it from maybe t1 to t, and this is, yeah, okay. So we're going to integrate this from 1 to t, right? Because we want, the initial condition is not at t equals 0, but it is at t equals 1. That's why we need to put the upper and lower limits here accordingly. Because if we start from 0, we need to know r at 0, but we don't, right? That's why I put 1 there, okay? So integral v, yeah, it's just, so we are integrating 3t to the power of a half, right? Yeah. So that's going to be 3t to the power of 3 over 2 divided by 3 over 2. So that's going to be 2t to the power of 3 over 2, right? Just do the math there. I then minus t squared j, just integrating to t. Okay? And we're going to sub in the bounds of 1 to t, like that. Okay? So if we just find a change in displacement from time 1 to time t here, it's just going to be, well, it's just 2t to the power of 3 over 2. And if we sub in 1 directly to the I component, we get minus 2, right? Just do each component separately. Yeah, subbing in 1, you get minus 2 there. And for the j component, we get t squared here, right? So it's minus t squared. And, okay, I'm just going to do this. And then you have a minus 1 there in there. So we have this, right? So it's just like that. Yeah? Okay. So I think we're done with the change in position vector now. So r at t equals t, then it would be r at t equals 1, which is minus j. Yeah. So I'm just going to merge the component already because this is just minus j. It is not that complicated. So minus j is minus 1, right? So it's just so if you add a minus 1 into that, you're gonna get, this is basically just minus t squared plus 1j, right? So it's just minus 1, so you're gonna get minus t squared j, just that, because the minus 1 will cancel with the plus 1 there. Yeah. All right. So that is r at time t. Yeah. That's just done, actually. Meters. That's it. Part D. Find the exact distance of P from O at the instant when P is moving with speed 10. All right, this is 6 marks. Okay, so the exact distance from origin, OP here, so because we already got the position vector RT, yeah, we want to know the distance. So, but this is when P is moving with speed 10. So we got to go back to the velocity vector, right? To find that at what time it is moving at the speed of 10. And again, the speed is just the magnitude of velocity. So we need to find the Pythagoras of both components, being 3t to the half squared, yeah, and then plus 2t overall squared, like that. And we're going to equate this to 10. So if we square both sides and we simplify the part here, we're going to get 9t plus 4t squared equals 100. Yeah. And then if I do a quadratic here, I get this. Right? So if we solve for t there, we're going to know the time. And we use that time to find the exact distance. So let me just use my brain to factorize this maybe, if it's not too hard. Let's try 50 and 2, no, 25 and 4. Yep, 25 here and 4 here. That's going to give me plus here and minus here, right? Let me just double check that. Yeah, that works. Minus equals 0. So time is minus, well, 4 first and then minus 25 over 4, which we reject. And then we're going to use this time to find the r at t equals t. So we're going to use r4 here. Just use this equation we found earlier. So that's going to be 2 times 4 to the power of 3 over 2 minus 2i minus 4 to the 2, which is 16j. Yeah? And work out that vector. We get, well, 4 to the power of a half, we get 2 first. And then 2 to the power of 3 is 8. 8 times 2 is 16. 16 minus 2 is 14. And that doesn't change. So the exact distance, OP here, would be just the modulus of that R4, which is the Pythagoras of 14 and 16. Yeah? The exact distance. Okay, here we go. 14 squared plus 16 squared. Can that be simplified? Let's find out. Yep, 2 root 113 meters. Yeah. Okay. Let's go to the next question on the next year now. This is 2022. I guess June. Yeah, June 2022. Question 3. Yeah. Particle P of mass 4 kilograms is at rest at the point A on the smooth horizontal plane at time t equals 0. Two forces F1 and F2 where lambda and mu are constants are applied to P. Given that P moves in the direction of vector that, show that blah blah blah. Well, this one is interesting because there is that part A there that I saw. I think I picked this because of part A. So you need to use what? Sigma F equals MA, right? But then how are you going to connect the whole story? Because usually when you have the direction of vector, that is indicating the direction of motion. So usually you would think of velocity, but there is no velocity here. Actually, when you have forces and resultant force, it is going to lead to the acceleration first. But because the object here starts at rest, so whatever the resultant force you are giving to it at the very initial time, that's going to be the direction at which it's going to, right? That means we need to find the acceleration and make it parallel to that vector to find, the lambda and the mu. All right, that's the plan. Okay, so A, we find the resultant force equals ma. So A is just resultant force, which is 4I minus j plus what? Lambda I plus mu j, right? Divided by the mass, which is 4. Yeah. Okay. And if we simplify that, we are gonna get for the I component is just 4 plus lambda over 4I. For the j component is just mu minus 1 over 4j. Now, because this is to be parallel with vector 3i plus j, right? So it's just 4 plus lambda 4I plus mu minus, what is that, 1, right? 1 over 4j is just some constant k times the 3i plus j, just the same way I did before, right? So we're gonna say that, okay, so 4 plus lambda over 4 equals 3k. This is vector method. We just look at the two components separately because they must be equal. So I can equate the I component from the left vector to the I component of the other vector. Yeah, and that's just one equation there. So this is if we simplify this, we get 4 plus lambda equals 12k. That's the first one. And then this is the I component. So the j component, yeah, is just mu minus 1 over 4 equals k with no 3 there because that's just a j, yeah. So mu minus 1 equals 4k, yeah. And now if you combine, no, not combine, you gotta eliminate k, right? So if I multiply that by 3, I'm gonna get 3 mu minus 3 equals 12k. And you can equate these two, right? So if you equate those two, you get 4 plus lambda equals 3 mu minus 3, right? Because they equal there. And that is probably going to lead us to that equation. So if we move everything on the same side, lambda minus 3 mu plus j equals 0, yeah, as required. That's it for part A. Part B. At time t equals 4, P passes through the point B. Given that lambda equals 2, okay, find the length of AB. This is also interesting because when it says lambda equals 2, of course, you can find mu. And then the two forces will be revealed. Hence, you can find the resultant force. Hence, you can find the acceleration. And how does acceleration have anything to do with finding the length AB? Well, think about it. The length AB is kind of like displacement. Yeah, you're going from A, which is assuming the starting point, point A, and then go directly to B, right? So you're finding displacement at time t equals 4. So 4 seconds has passed, right? So we're gonna find the acceleration first then. So if lambda equals 2, then mu equals, just gonna solve for mu first. So mu would be lambda plus 7 over 3. Just solving this equation here, guys, yeah? All right, just checking. Yep, and that would be 2 plus 7, 9 over 3, that's 3, okay? So the acceleration, right, we got an equation earlier, is this guy here. So 4 plus lambda over 4, 4 plus lambda over 4i plus mu minus 1 over 4j. Mu minus 1 over 4j, right? That's it. Just checking. Yep. So that is just what? 1.5i plus a half j, right? That's just the acceleration there. Okay, now we got the acceleration. Particle P starts assumingly from point A, which is treated as an origin maybe, and then you want to find displacement. So we can use Suvat. So S equals, yeah, ut plus half at squared. Okay, and everything will be treated as vectors here. So S is the vector, like the relative vector from A to B. Yeah, so this is A to B. Yeah, U is the initial velocity. It's 0. That's easy then. 1/2 A is just not 1.5 and 0.5 here. And T squared is just going to be time 4 squared. There you go. Yeah, that's just vector AB. That's easy. So you have 16 here, and multiplying a half here, you get 8. So 8 multiplying in, you get 8 times 1.5, you get 12. And 8 times 0.5, you get 4. Yeah, that's the relative vector AB. So the length AB will be the magnitude of this vector, isn't it? And that's the Pythagoras of those two. So that's 144 plus 16. That is 156, right? Let me just check a calculator here. 144 plus 16. No, hang on. 144 plus 16 is 4 root 10. I'm just going to make that 12.6 meters. Yeah, so that is just part B done. Now let's have a look at the next year, June 2023. Yes, starting from the first question. Seems like a projectile question again. Question 5. A small ball is projected with speed 28 from the point O on the horizontal ground. After moving for t seconds, the ball passes through point A. The point A is 40 meters horizontally and 20 meters vertically from point O. Right, we can see from the diagram here. The motion of the ball from O to A is modeled as that of a particle moving freely under gravity. Given that the ball is projected at the angle alpha to the ground, use the model to show that T is 10 over 7 cos alpha. Right, so because it's given us the displacement on both components, we're going to use that. So this is, hang on, June 2023, question 7, in it? 5. Okay, so part A, yeah? Well, yeah, so Sx, which is the horizontal displacement, being 40, is because the horizontal speed is constant, right? And it is 28 cos alpha times time. Yeah, and that is just the capital T there. Yeah, after moving for t seconds. So I'm just going to use the capital T. Now, as you can see, right, because in part A it's just 2 marks and seems like I can just rearrange to make T the subject from there. So I get 40 over 28 cos alpha. And if you simplify that using 4, you're going to get 10 here and 7 down here. And that is just as required, right? Okay, so part B. Show that the tan squared alpha minus 4 tan alpha plus 3 equals 0. Now this will involve the vertical motion as well. So for Sy, right, usually we use the Suvat equation, the S equals ut plus half at squared. So S equals uyt plus half ayt squared. So Sy is 20 positive. Uy is just 28 sine alpha, right, times t, which is the capital T as well, plus half a is minus 9.8, right, t squared. Let's see, so we need to show that this is quadratic. It seems like we need to substitute this whole thing into the t because we don't have the t in that equation in part B, so we're going to do that, right? So I'm just going to do 20 equals 28 sine alpha times 10 over 7 cos alpha, and that's going to make 110 there, plus And this is, if you simplify the numbers there, you get minus 4.9. Sorry, so that will be a minus. And then t squared, right? So t is again 10 over 7 cos alpha. So it's just going to be 100. Sorry, 100 divided by 49 cos squared alpha. Okay. So if we simplify again, we get 7 cancel 28, we get 4, so that's just 40. Sine over cos is 10, right? There you go. We get 110 there. And of course, we will simplify this again. And here, 4.9 cancel with 49, we get 10 down here. So 10 cancel with that 10, we get 10. But 1 over cos squared is just sec squared, right? So this is secant squared alpha. But from trig identity, yeah, we know that sec is just 1 plus 10, yeah? So 40 tan alpha minus 10, 1 plus 10 squared alpha, right? So if we cancel all the 10 as well, we get 2 equals 4 tan alpha minus 1 minus 10 squared alpha. Okay, so simplifying that, we should get tan squared alpha on the left, moving the 4 tan on the left as well, and then moving the minus 1 to the left, we get a plus 3 equals 0. So that's it. That's the required equation there, which we show. Okay, part B is done. Part C. Find the greatest possible height in meters of the ball above the ground as the ball moves from origin to A. Greatest possible height is just the turning point here, right, guys? So at this point, the vertical velocity is 0, yeah? And then we can find the greatest possible height. So if we do suvat, we want this guy, yeah, we want this guy, and then u is just the vertical speed, the vertical initial speed, which is just 28. What is that? Sine alpha, right? V is 0 there, and A is minus 9.8. Well, t we don't know, we don't care, so the only suvat equation without the time would be v squared equals u squared plus 2as, which is the h here we want to find. Now the sine alpha, right? It seems like because we got the equation of tan alpha earlier, I think we need to solve that first to get the alpha, because we don't know it yet, we need it, yeah? So from that equation, right, in B, we can factorize quadratically, hopefully, and that is just minus 1 and minus 3, right? Yeah? And then we're gonna solve for the angles here. Note that, well, we have tan alpha equals 1 or tan alpha equals 3, right? Well, for tan, it's just similar to sine, isn't it? So the greater the angle, the greater the number, right? Because tan 0 is 0, so it's just like sine. So that means for tan alpha equals 1, the alpha will be a small angle. For tan alpha equals 3, the alpha will be a larger angle, right? So does it matter here? Let's see. If we change to sine, yeah, what should we get? All right, so if we solve for both angles first, so I'm just going to do arctan 1 here. That's 45, right? Or alpha equals arctan 3, that's 71 degrees, so 565. I'm going to keep it as that. Okay, so we're going to plug that into the u. So let's plug the, yeah, I think, so we're going to greatest possible height. Well, let's see the equation. So S here, which is the h, yeah? If you rearrange that equation, you get v squared minus u squared over 2a. So a is 0. So yeah, so u squared is just 28 squared sine squared alpha divided by minus 2 times 4.9. Sorry, 9.8. So you see, the greater the sine value, the greater the maximum height. So we need the alpha so that sine alpha is greatest. And that's going to be 71 and not 45, right? So we're going to use that. Yeah, so this is 28 times sine 71.565, right? So I'm going to answer that first and do 28 times sine answer. Yeah. And that's going to be 26.563. I'm keeping that and do that. So that's going to be equal again, clear. Wait, what? Yeah, sorry. So minus 28 squared. No, I'll take the minus out. 28 squared times. Okay, I think I should use the whole of that, right? Because that's u sine. That's u, yeah. So this is just follow through from 26.563 squared, right? Yeah, gotta be careful there. And this is over 2 times 9.8. So that's just 35.999. That's about 36, right? So that's 36 meters, the greatest height. And that is just part C done. Now part D is just answer one marker here. The model does not include air resistance. State one other limitation of the model. Well, again, this is about assuming that the ball is a particle. So again, guys, you should be getting used to this. It's just that if we ignore the volume or the shape of the particle, we ignore other types of movement like rotation along the way. So the model does not account for the shape or rotation during the motion. Yeah, and again, G might not be 9.8 and so on, right? So that's it for this one. Let's have a look at the next question, number 6. A rod AB has a mass M and length 2a. The rod has its NA on a rough horizontal ground. The rod makes an angle theta with the ground as shown in figure 3. The rod is at rest in limiting equilibrium. A, state the direction left or right on figure 3 above of the frictional force acting on the rod at A. Okay, so number 6, part A. The frictional force acting on the rod at A. Okay, so you need to look at this as if reality here. This is reality. So if you let this ladder go, it's a rod, but yeah, let's say it's a ladder. It would fall off rather than sliding up, right? If it were to slide up, that would be kind of like ghosting that. So it could fall off. Why? Because there might not be enough friction on the wall and on the ground. Let's say the wall as well as the ground were smooth, but in this case it's just a rough ground but smooth wall. So okay, the wall is smooth, but let's say the ground is also smooth. So it's gonna fall. 100% it's gonna fall. Common sense, right? The fact that we can lean the ladder on the wall because the wall is kind of like rough enough so that it holds the whole weight of the ladder, also the ground. So that means the attempting motion, yeah, if you like, the attempting motion would be trying to slide the ladder downwards, so the NA will sort of move to the left. Yeah, it's going to move to the left. So that means the friction will try to stop that movement. So friction would have to be to the right from point A. Yeah? So we say that because there is an attempted motion, there is an applied, yeah, a better word, applied force from well, in this case, if we look at all of the reaction here, so if we draw a free body diagram, so you have a normal reaction there, and let's say I'm drawing at B first, you have a reaction at B, yeah, a normal reaction at B. Well, the B doesn't have any friction, so, and then you probably have a weight here, mg. So you see, it is not possible to hold this shape because there is a leftward reaction force at B. So to balance that, you need a friction to go against that, right? So we can say that there is a reaction, yeah. There is a normal reaction at B to the left, right? So to balance that, friction must be to the right. That's it. That's part A, yeah. Part B, the magnitude of normal reaction of the wall on the rod at B is S, yeah, so that's S instead there. Okay, we're going to use that. So this is part B, and that is S. And then we need to show that by taking moments about A, well, that's convenient, that S equals half mg cot theta. The coefficient of friction between the rod and the ground is, oh wait, sorry, that's it. So part B is just that, all right. So taking moment about A, yeah, okay. So at A, we have the weight, mg. It's actually a capital M, yeah, and G there. I'm just going to write that again. And is the rod uniform? Is it uniform? Just checking here. Rod AB has mass M and length 2A. Yeah, being uniform here. I didn't see that. Okay, this one here. Okay, so that means the weight is going to be acted at the middle, which is A from A. But we need to know this theta, angle theta. Well, we don't have to know it yet because this is, still theta here. So the clockwise moment is just then mg times A cos theta. Yeah, just the perpendicular distance here. I would like to resolve distance rather than force, right? So this is already the force. You just know this distance, which is A cos theta. Equals, and then you need this force and its perpendicular distance here. So that's just S times, well, this is going to be, because this whole lot of length is 2A, so that's just 2A sine, right? So it's 2A sine theta times S. Yeah? And that's just easy. You just make S the subject. You cancel the A. So S is just 1/2 mg cos theta over sine theta. And that is just 1/2 mg cot theta as required. That's not bad. Next part is C. The coefficient of friction between the rod and the ground is mu. Okay. Given that tan theta is 3/4, okay, find the value of mu. All right. So again, the little triangle trick. I mean, barely they never ask you to find the angle, right? So we're gonna do it like this usually. And as you can notice, they are usually using 3, 4, 5, right? That's very classic one. So that means sine theta is just 3/5. Cos theta is just 4/5. Yeah. So we already get the cot there then. So we know the S. So we want to know about the mu. So let's do force along the x-axis, equilibrium of the horizontal force. So we only have 2 forces. So the friction must be equal to the S, right? And friction is just mu times N, right? Equals S, which is 1/2 mg cot theta. Yeah. but we don't know n yet, so actually we should get n from the y component. So fy, so y component is just n equals mg, yeah, that's it, right? Because we only have the weight and the n. Okay, now just plugging n in there, so mu equals mu mg equals 1/2 mg. Well, cot theta, right, is just 1/tan, and tan is 3/4, so cot should be 4/3. Mg cancel, so mu is just 1/2 times 4/3, so that's 2/3, right? That's the value of mu for part C. Part D. Find in terms of m and g the magnitude of resultant force acting on the rod at A. Well, resultant force, right? So F, the friction first. So we have at A the friction and the friction to the right and normal reaction N. And we remember that N was mg and friction was S, right? Yeah. So in terms of m and g, right? So F is again mu n. So n, yeah, we can just use S, right? I mean, they're gonna be the same. So I'm just gonna take this one. So that's 2/3 mg, which is the same. And n was also mg. So if we do a Pythagoras of that one, we're gonna get the resultant force. Okay, so F at A is just the Pythagoras of 2/3 mg squared plus mg squared, like that. Well, the mg squared can be factorized out. So you see, if you imagine you're going to have mg squared on both terms, and when you take out of the square root, it's just going to be mg. So actually you are doing the numbers here, 4/9 plus 1. Okay, and we want in terms of n and g, yeah, the magnitude of the resultant force. So I'm just going to do, what is that, root 13/3, right? Because root 9 is 3, yeah, mg. So I'm going to leave my answer like that for part D. And then part E. In a new model, the rod is modeled as being non-uniform, with its center of mass closer to B than it is to A. Now this is similar to another question in the other year, and it's going to ask you probably the effect, right? A new value of S is calculated using this new model with tan is the same, 3/4. State whether this new value for S is larger or smaller or equal to the value that S would take using the initial model. So it's just asking what will S be. So if we look at the S again, S was just 1/2 mg cot theta, right? Well, look, we got this S. Well, it seems like there is no location of center of mass on this one, right? Like it's not dependent upon the location of center of mass. Well, let's have a look at how we got S in the first place. We got S from resolving the moment here, right? Yeah, if you only look at the equation without looking at how it came from, where it came from, then you might get it wrong. Because look, if mg is now closer to B than to A, so B is here, so mg is now probably around here. Okay, and this value will increase. So the distance, the perpendicular distance here, so this perpendicular distance of the weight component will increase, which is that guy right there. So that will now be, say, something more than 1. So let's say 2a, yeah? Let's say 2a, that means the S here will increase, right? Because when you cancel the thing, so let's say I have a 2a here, 2 will cancel, you will now have an mg cos theta over sine rather than half. So basically, if this side increases, S will also increase. Yeah, because this is the same, isn't it? So the 2a here at the S is still the same, but the location of the mg here increases, so that term increases, that makes S increases. This whole term will be a new one. So you can't just look at that previous equation. You got to look at where it comes from, right? Yeah. So S will be larger then if if m is closer, if mg is closer to b. So yeah, so S is larger for this. Yeah. Now let's reason this physically and not mathematically, right? Because we need to give the reason. S is larger because we're gonna have. So if you imagine here, mg will be moved closer up to b. Because we have a greater weight, moment of weight here. The greater, so the moment by weight will be greater at A. Yeah. So to balance that out, the S, which is the normal reaction, will have to increase at the wall. Yeah. So I'm just gonna do because there is a greater moment due to weight at A. Yeah. So the reaction, so the counter clockwise moment from the reaction at B must be greater. Therefore, S is greater. Like that. Okay? Let's go to the next year. Now, this year, June 2024, I have already walked through the paper, the entire mechanics and statistics paper. But I'm going to attach the link in the description to the particular question here, there's only two questions, right, that are interesting. Still the vector equation there, because you can't be too careless about vectors there. Number 4 here, and also number 5 here. This is also very interesting actually. So you can check the links in the description to these 2 questions, right? And I hope that was all useful. Please like or subscribe, or maybe do both if you love me. And don't forget to stay tuned for the next video. Bye.